All right, so let's talk about solving linear systems. You have solved linear systems in Algebra 1 using graphing, substitution, and elimination. So we're going to revisit some of that, but we're going to look at it in some new context here for Algebra 2. So just to recap on what we did in our previous lesson, we used the graph to solve equations. 1x plus 3 equals x plus 1. And looking at this graph, we would see that their intersection occurs where x equals 4, which means the solution to this equation, let me go underneath it, is x equals 4. Notice that the equation itself only has the variable x, so we only need to solve for x. Now the system of equations here, a lot of times they use curly brackets to group them together. The system of equations would be y equals 1/2 x plus 3 and y equals x plus 1. Notice that this time for this system, so I would label this as a system, for this system, we have two different variables. So we have y, but we also have x that we're solving for. So when we name our solution to this system of equations, we should be naming an ordered pair. So in this example, my solution is 4 for the x value, but we are also going to name the y value, which in this case is going to be 5. So my solution would be the ordered pair for 5. All right, so you should have a quick sketch of that, but you should definitely make note of the fact that solutions for systems are ordered pairs. All right, so we have graphing, but we also need to be able to solve things using algebra. So remember, using algebra, we have two options. We have substitution and elimination. And in this example, I would like to show you how to solve this with, actually with both. So I'm going to start with elimination because I think that's where this is set up best for. I notice right off the bat when I try to look at these two equations that they have opposite y values. So if I were to add the equations together, these y terms would actually cancel out. So that's what I'm going to do. I'm going to add these two together. It's going to give me 2x equals 7. I can divide by 2 and go ahead and solve for one of my values, and that's that x equals 7/2. Now, to find my y value, I can plug that back in. So I'm going to use either equation. I'll plug that back into the x spot. So this is 7/2 plus 2y equals 3. And then I can solve that out. And those of you that have had me before know that I don't like fractions, so I'm going to multiply to get rid of them. 7 plus 4y equals 6. Subtract 7 from both sides. And then divide by 4, which is going to give me y equals -1/4. So for this system of equations, my final solution, again, is going to be written as an ordered pair, and the ordered pair is 7/2 and -1/4. Make sure you put the x in the x spot and the y in the y spot. All right, now let's solve this using substitution. My goal here is just to prove to you that we're going to get the same solution and to show you another method. So for substitution, we're going to substitute one of the equations into the other. The first thing that I notice here is that I can rewrite this second equation so that it tells me what x equals. So if I add 2y to both sides, this equation becomes x equals 2y plus 4. Now that I know what x equals, I can substitute that into the original equation. This process of substitution is then going to give me the equation 2y plus 4 plus 2y equals 3. I can combine like terms and subtract the 4 to the other side. And this will give me that y equals -1/4. Which should check because that's what I got on the first one. And then I can plug that back into one of the equations just like I did before to solve for x. So I can do x plus 2 times -1/4 equals 3. X plus, this is -1/2 equals 3. So x equals 3.5 or 7/2. So again, I'm getting the same answer with this other method, and you've learned this in Algebra 1, but some methods are easier at different times, but you should be sufficient solving both directions. So now let's talk about solving a system of linear inequalities. So inequalities now, not equations. Our option to do this is really just to graph. So we're going to do that here. So this problem says Malcolm earns $20 per hour mowing lawns and $10 per hour walking dogs, and his goal is to earn at least $20 each week. So if I write that as an inequality, that's going to be $20 an hour mowing lawns, so I'm going to use an M, and $10 an hour walking dogs, use a D, needs to be at least, so greater than or equal to, $200. He can work a maximum of 20 hours a week. So he can work a maximum of 20 hours per week, which means the amount mowing plus the amount walking dogs can be no more than, so less than or equal to, 20. It's also true that Malcolm must spend at least 5 hours per week walking the neighbor's dogs. So the amount he spends walking dogs needs to be at least 5 hours per week. So based on this right here, you should be kind of making a mental image that we're going to create a graph that has 3 different inequalities on it so that we can answer this question. So I'm going to set up our graph for us. So as a reminder from Algebra 1, when we're graphing things that are in standard form, one of the easiest ways to do that is to do intercepts. So in this first equation, the 20m plus 10d is greater than or equal to 200. If all he did was mow lawns, he would have to mow 10 lawns. All right, so here's my point at 10. If all he did, and I'm going to count by 5s here, if all he did was walk dogs, then he would have to walk 20 dogs. So 5, 10, 15, 20 dogs. So that's going to help me create one of my inequalities. And if you remember from Algebra 1, we're going to have to do shading here. Greater than or equal to means we're going to shade above. So I'm going to use this to shade above. All right, now let's talk about how to graph this one. If all he did was he could either spend 20 hours mowing lawns here or 20 hours walking dogs. So 20 hours mowing lawns, 20 hours walking dogs, still at 20. And this one is less than or equal to, so when we shade this time, we're going to be shading below. And then lastly, we have this stipulation that he has to spend at least 5 hours walking the dogs. So on the dogs, we're going to have 5 hours that he's walking the dogs, and at least for this one means we're going to end up shading above. Now, this might look like a mess, but hopefully you can kind of see in this area that there is a specific section where all of these 3 things overlap, and that is this section, having a lot of trouble drawing that, right here in the middle. And so what that means is that anything in this area is going to be our solution set. So you should label here that this is our solution area. And so there's lots of different possible combinations, but solutions would be any ordered pair within that set. So in this example, we're going to talk about how to represent a system of equations using a matrix. So a matrix is something we're going to talk a little bit more about. It is a rectangular array of values, so it will look like something in these kind of brackets that has a sets of values in them, almost like a spreadsheet or like a table, but not that. And we use it to represent a system of linear equations. So the first thing that we need to do, you should copy down this original system. The first thing that you might notice is these do not line up. So what I need to happen is I need all of these equations to be in standard form. That means I need them in a form that says ax plus by equals a constant. So what I'm going to do is take a minute to fix these equations so that I can have that happen. So to fix my first equation, I notice that the x term needs to be moved to the left side. So to move minus 2x, I can add 2x to both sides. So this now will say 2x plus 3y equals 1. And in the bottom equation, I notice that the y is in the wrong place. It needs to also be moved to the left. Because that says plus 2y, I'm going to subtract it to the other side. So this second equation is going to say, and that's a y, I'm sorry, is going to say 4x minus 2y equals 10. Notice that now in my equation, my x's line up together, my y's line up together, and then the constant terms are on the other side of the equal sign. All right, from that, we can write what is called an augmented matrix. And we're going to do that using the coefficients. So notice it's in this order, and I'm going to write the coefficients from the first equation. They are 2, 3, and then we're going to use a dashed line to show that we're on the other side of the equal sign now, and a 1. In the bottom equation, this would become 4, -2, and 10. Things to note, this top part, right, these are my x values. The next column are my y coefficients, and the last column are my constants. That says constant, that's a C. Also, I want to tell you how a matrix is named. So matrices are named using rows and then columns. So matrix dimensions are row by column. So remember, rows go side to side, columns go up and down, they hold the house up. So this specific matrix is it has 2 rows and 3 columns, so we call it a 2 by 3 matrix for this specific example. And later on in Algebra 2, we're going to learn what we can do with matrices and how we can use them to actually solve systems. All right, for the last part of this video, we're not going to go all the way through this example, but what I would like for you to do is writing down solving a system in 3 variables. So you can copy this system down. And then some things I want you to know. If there are 3 variables, this means that you should have in the end 3 solutions. And we don't name these as ordered pairs anymore. We name them as what's called an ordered triple, where your answer would be X, Y, and then Z. The last thing that I want you to write down with this example is that to solve this, the only method that you know right now is we can use a set of substitution and elimination. And we will work on this together when you come into class tomorrow.